to another lecture on molecules in motion. In the last class, what we were talking about was how to determine the transport number. Transport number, as you remember, is defined as the fraction in which we express the amount of current carried by each of the ion. Okay. So, we have seen from the independent migration of ions, if we apply the Kohlrausch's law, then measuring of the transport number can be used by using various expressions. So, we have seen how the transference number or transport number can be expressed as the ratio of the fraction of current carried by the positive ion by the total current passed through the system. Similarly, if we have also seen that the transport number can be also given by the this is the number, stoichiometry number, the formula unit of the electrolyte, which is going to give rise to the number of formula or cation or anion for a particular electrolyte system, that into the ionic conductivity divided by the molar ionic conductivity of the electrolyte. That is another method of finding out the transport number. So, and also we have seen that if you take the ratios of the ionic mobility of any of the ions divided by the ionic mobility of both the ions present in a system, we were essentially talking about electrolyte, one type of electrolyte where we can generate one type of cation and another type of anion. We are not talking about any mixed system where we have the electrolyte dissociated, two type of electrolyte dissociated or three type of electrolyte dissociated, giving rise to a number of cations and anions in the system. We have also seen that the transport number can be given by the ratio of the drift speed of the cation or the anion divided by the drift speed of the total ions, cations and anions present in the system. And if you remember, this transport number we have associated with the condition where the concentration is approaching 0, that means infinite dilution. So, the plus minus sign essentially is clubbed together. These can be separated for individual contributions. So, for convenience we have written plus minus. If this is plus, this is obviously going to be plus, this is obviously going to be plus, and this is obviously going to be plus for all the numerators. Similarly, if we have the subscript minus, that means corresponding to the anion, then it will be the current carried by the anion. Here it will be the ionic mobility of the anion and the number of anions generated per mole of the electrolyte. Here will be the mobility, ionic mobility of the anion. So, will be the ionic speed. Okay. So, this is the ratio, and we are essentially going to use the ratio of the, we are going to find out the fraction of the current carried by the individual ions. And since the number of electrolyte we are dealing with is 1, so the fraction of current carried by the anion and the fraction of the current carried by the cation, if they are added, should be always equal to 1. They are the fractions, so the total should be always 1. We have talked about how to go about the measurements of the transport number for an electrolyte system. In the last class, in the previous lecture, lecture 24, we have discussed the moving boundary method. In today's lecture, we are going to take up another method. In fact, this was the method which we began with to find out the transport number. It was the Hittorf's method. It is the Hittorf's method, and Hittorf was the first person to put forward the measurement of the transport number for a particular system, even before Kohlrausch's law was established in independent migration of ions was established in full form. Okay. So, the Hittorf's method, if you can see, this is the Hittorf cell which we are talking about. In this Hittorf's method, unlike the moving boundary method where you had two types of solution, the lead solution and the indicator solution. And what we had discussed in that class, that we had a common anion, two salts were used, two electrolytes were used. One was composing the lead solution and another salt was composing the indicator solution, but both these electrolytes had a anion common, and if we had an anion common, we were actually determining the transport number of the cation. Unlike that, what we have in this Hittov's method is a electrolysis cell. This is the electrolysis cell we have, and we measure the transport number, the contribution of the current carried by each of the cation and anion in the system of the total current we do is through the Hittov's cell. Okay. What you have? We have a electrolyte system. Suppose the electrolyte system which we have is copper sulphate. Okay. And the cathode and the anode which we have here, we have, if you see this system of the electrolysis cell, you have the cathode here, you have the anode here. This portion is known as the C, we can nomenclate it C. We have nomenclated this part as A and this part as B. Now, what we have? We have electrodes which are made of copper, and the electrolyte we are using is copper sulphate. What we are going to monitor? See, if you see the Hittov's cell very carefully, we have compartmentalized the cell into three parts: A, B and C. A is the cathode compartment, B is the anode compartment and C is the middle one. So, what we have? We have three compartments. Now, we see, and each of the compartment will have the electrolyte copper sulphate. So, now what we are going to see is the change in the amount of copper sulphate in each of the three compartments on passing of 1 mole of electricity. Now, according to the definition of the current passed or electricity passed, if Q is the quantity of electricity passed, then Q by F, F is the Avogadro Faraday constant, is the moles, and all of these changes which we are going to see for the amount of copper sulphate in each of the compartment, hence should be multiplied by Q by F. Okay. So, the moles which is changing is Q by F when Q amount of electricity is passed, right. So, Q by F is the fraction of the mole which is the mole which is generated when you have Q amount of electricity passed. So, the changes whatever you see in the amounts of copper sulphate for each of the compartment should be multiplied by Q by F to get per moles, or the moles of the changes in the moles of the amount of copper sulphate. Okay. So, this is to simplify the whole thing, so that you have all in one unit in moles, and if Q is the amount of electricity, then Q by F, F is the Faraday constant amount of the moles which is bringing about the change. So, we have to multiply Q by F for each of the changes which we see for the amount of copper sulphate. Clear? Now, what we see in this, that by arranging the apparatus properly, the boundaries between A, B, C can be replaced by the stopcock. See, in previously we had a boundary generated by the mobilities of the ions and the densities of the electrolyte solution. Here what we have separated out the three compartments. You see, for the compartment 1 I have put a stopcock, and so this whatever solution concentration is there I can monitor here. Similarly, for the anode compartment we have a stopcock. So, all of the solutions in this is going to be retained in this. We can see the changes in the concentration of copper sulphate here, and then you have this section which is the middle one, which is having the electrolyte copper sulphate, and we have stopped separated the compartment by a stopcock. So, I have three distinct boundaries differentiated by using a stopcock, so that each of the portions I can have a amount of the electrolyte taken out from this or this or this and find out the amount of copper sulphate that has changed. That means, what I need to know, we need to know the amount of copper sulphate which was initially present. So, that obviously can be done because we are making the solution. So, we are putting the electrolyte into the Hitov cell. So, the initial concentration of copper sulphate should be known to us. Now, as you see, we are going to look into what is happening. You have the anode compartment, cathode compartment, you have the anode compartment, and both of them are made, the electrodes are made up of copper. So, the solutions are separately drawn from each of the three portions after the experiment is done, and either we weigh or find out the concentration of the electrolyte in each portion and then analyze our data. The changes in the number of moles of the electrolyte in each compartment can be obviously known from the knowledge of the original concentration of copper sulphate in each of the compartments. So, what we have here, you just see, we have the deposit in the cathode section, we have deposition of the copper ion. What is happening in anode? Anode, you have this as the copper electrode. Here what happens, the copper ions get dissolved in the electrolyte solution, and here what you have, the copper ion present in the electrolyte solution is deposited onto the electrode. So, obviously, you see what happens when you see the three compartments. Here you have a deposition, here you have a dissolution. So, if I have three compartments, like this is the compartment A, this is the compartment B, and this is the compartment C, what should happen in this compartment A? If you look at it very closely, since the amount of copper is getting deposited, so what should happen? There should be a depletion of the amount of copper sulphate in the compartment which is having a cathode, right, because we have a deposition here. So, the amount of copper sulphate which is present is getting deposited. So, obviously, the amount of the copper sulphate concentration in this compartment should decrease. And what happens to this part, the cathode anode part? Anode part is what is happening, there is a dissolution of the copper. So, the copper ions from the copper electrode is dissolved into this compartment. So, as the experiment proceeds, what we expect is the compartment which is cathode to have a depletion in amount of copper sulphate in this compartment, while the compartment which is anode should have an increase in the concentration of copper sulphate in the after passage of current or passage of electricity on performing the experiments. So, and we have seen that if we want to find out what is the change of mole if Q amount of electricity is passed, we want to see the changes in mole. So, whatever we have said in the just now, that each of the changes whichever we are seeing, the amount of copper sulphate in the cathode compartment, this is the cathode compartment where you will have a depletion, decreases by how much amount? This fraction should be multiplied by in both a cathode and anode compartment. Q by F gives you the moles. So, Q by F moles into what? I know the transport number divided by the Zi. So, if Z plus T plus is the transport number, transference number, whatever you call, per the cation charge of the cation Z, this is the if this is multiplied by Q by F gives you the amount which is now present in the compartment, which is a decreased amount which is present in the compartment cathode. While what happens in the anode? Sorry, this should be a negative sign. So, the anode compartment, what happens? You have an increase in concentration. For what happens? 1 by Z plus moles of copper plus 2 ion dissolved. So, what is the total change in moles? This into the transference number, that is the T plus ions into divided by the say the charge of the plus 2 ion into the moles of the if q moles of electricity is q amount of electricity is passed. To find out the mole change in moles, we have to multiply by q by f. So, we have this for the in the anode cathode compartment, we have this for the anode compartment. Now, what happens in the middle of the middle compartment? If you just have a look at it, this is a zone where the migrations are taking place. Here in this portion, you will have a amount of copper ion migrating from the anode to the cathode, and here you have this sulphate ions, where you have the sulphate ion migrating from the cathode to the anode. So, virtually what you should have, that the copper sulphate concentration in this middle section should not have any change until you have a transference which is generated. So, you have a look at this, what we have seen. We are saying how many moles of the copper is dissolved. We say if the charge of the ion is Z, then 1 by Z moles of copper is dissolved and 1 by Z plus moles of copper is deposited. The same amount should be is expected to be deposited in the cathode compartment, and this amount 1 by Z moles of copper 2 salt should be dissolved in the anode compartment. And what happens to the anion? The anion, which is you see it is getting deposited. You have a copper sulphate system where you have copper plus 2 ions and the sulphate ions. Now, the copper is getting deposited. So, the excess we have to maintain the charge neutrality. So, to maintain the charge neutrality, what you have, the sulphate ions, which should be becoming excess in this compartment, should start moving from the cathode compartment towards the anode compartment, because you see here you have generated more of copper 2 ions and not sufficient amount of sulphate ions are present. To maintain the charge neutrality in the entire electrolysis cell, we have to have a migration of the anions from the cathode compartment to anode compartment. So, what virtually is happening? We are having a cation movement from anode to the cathode, and we have an anion movement from the cathode to the anode, and this is like a platform through which each of the ions is changing from one compartment to other, right. So, if I want to see what is happening, so let us see in each of the portions of the compartment, cathode, anode and the middle section. What is happening? What is happening is we are in cathode compartment, we are having 1 by Z plus. Z is the charge of the cation which we are dealing with. So, 1 by Z plus moles of copper ions plated is deposited or plated on the cathode. Okay. And in the anode compartment, we have 1 by Z plus ion, that is Z is the charge of the ion which is cation which is getting dissolved from the anode. This is what is happening, and what is happening here, the fraction of the current which is carried when you are passing q amount of electricity, then this into the fraction of the transport number, the fraction current carried by each of the cation and anion has to be multiplied. So, this is the fraction which is multiplied with into the total charge which is carried 1 by Z. It gives you the moles into it has to be multiplied by q by f to get the total moles. So, T plus by Z plus is the number of moles of copper ion which is migrated from B to the compartment A. Okay. Now, what happens here? Again, what we see in the compartment in the cathode compartment, what is happening? That means, if this is the fraction of current carried by the cation, then T plus, that is the transport number of the cation, into 1 by Z should be the moles of the copper ion which is migrated to the section A, that is the cathode compartment. And to maintain the charge neutrality, the fraction of the current which is carried by the anion, T minus, into 1 by the charge of the anion, that many moles of the sulphate ion should migrate from the cathode compartment to the anode compartment. This is the thing which I am talking about. So, this is going to be, this is the amount which is going to be transported in, and this is the amount which is going to be transported out, right. So, what should happen in the compartment, middle compartment? Middle compartment, you will see that if you look at this, what is happening? These many 1 by Z plus, the cation of the which is migrated into the fraction of the current carried by the cation, that is the transport number of the cation, into Z plus T plus into 1 by Z plus of moles of copper will migrate from the anode to the cathode, passing through this place. Similarly, since 1 by Z minus is the charge of the anion which is present in the cathode, and the fraction of the current which is, if you pass electricity, the fraction of the current which is carried by the anion is T minus into 1 by Z minus, will be the moles of the sulphate ion which is present in the in excess in the compartment ion. In compartment A should be migrating to compartment B. So, if you see, this is the portion which is this side is migrating to this, this cation is migrating to the left side, and the anions are migrating to the right side. So, you can write down this as moles of the cations migrated out at A and moles of copper 2 migrated in at B. Okay. So, the sulphate ions are going to be migrating from A to B, and the anions are going to be migrating out of the B. So, the total anode concentration which we are going to be looking, we are saying that 1 by Z amount of charge is dissolved. So, what will happen if total current is carried by the T plus ion, then T plus by into 1 by Z of moles is migrating out of the anode compartment, and T minus by Z, the total current carried by the anion, that is the sulphate ion, is moving into the compartment anode, that is the B. So, now we see, take the note of what are the changes which has happened. We have the how much is deposited and how much is migrated of the cations and anions, and now take note of what are the changes which has made, which has been which has happened due to the electrolysis in the cell. If you understand, this is the platform in section C, or middle portion is the section. We do not expect any amount of accumulation of ions in this section, because this is only a platform through which the cations are moving from say anode compartment to the cathode compartment, and anions are moving from the cathode compartment to the anode compartment. So, this is virtually a place through which it is passing. So, analysis of the middle portion is only done to check if there is any interference effect generated. If there is interference effect, obviously you will not get the correct amount of the charge which you are expecting, because interference can be accumulation of ions or some other form of problems in the migration. So, what you see here, now let us see the changes in the moles of the copper ion at the cathode. Okay. So, what we have? We have T plus the fraction of 1 by Z minus 1 by Z moles, which is this is the amount which is migrating in, and how much is deposited, this is the deposition amount. So, we have this many ions. If you do the 1 minus T plus T, the transport number of the cation plus the transport number of anion should be 1. From that expression you get a expression like this. Have a look at it. Please try to do it along with what I am just now showing. I am not writing it since it is already there in the slide, but I hope you understand that why I can write T minus here, because T minus is nothing but because T plus and T minus is totally summed up is equal to 1. So, I can write down T plus minus 1 in terms of minus T of the anion. So, we have similarly we can see the changes in the sulphate ions. Sulphate ions also should be having the same changes, transference number of the anion into 1 by the charge of the anion. The changes in cation and anion's concentration in this middle portion should be 0, because we should not be expecting any sort of concentration effects or interference effect in this portion. If we have that, then we have to correct it with the change of current. And in the anode compartment, what we have? We have this many amount which is having dissolved, and how much is migrating out? The total amount which is migrating is the fraction of the current carried by the cation divided by multiplied by the 1 by the charge of this. So, this gives the moles which is getting moving out, and this is what is generated in the compartment. The difference should give the changes in the number of moles in the of the copper ion in the compartment anode. So, this is going to be how it is going to be represented. So, if I know this, then I can find out what is the change in the concentration of the sulphate ion. This is going to be the transport number of the sulphate divided multiplied by 1 by the charge of the sulphate ion. So, if I have all these monitored in each of the experiment, what I have, the changes in the number of moles of the electrolyte in each compartment can be related to the transference number of each of the ion by the procedure which we have just now taken. It is possible to write down, it is generally not, we cannot have an equation. It is not possible to write down a general formula relating the changes in the transference number, since whatever is happening in each case depends on the chemical changes that is occurring in the electrode compartment or the electrode reactions which are taking place. Changes must be figured out using the method which we have just now established for each of the compartment. The measurement of the transport number are made over a large number of concentrations of the electrolyte. Then what we do? We do a measurement, whatever value of T we calculate for each concentration, that we plot against the concentration square root of the concentration and in a linear dilute solution, and from extrapolation to a condition where C equal to 0, we obtain the transport number at infinite dilution. So, at each concentration, from each compartment we are finding out what is the concentration change, and from that concentration change we are trying to correlate the concentration change with the transport number, and those transport number which we have calculated for each set of concentration of the electrolyte, we are plotting it versus C under root concentration under root of the concentration of the electrolyte, and from extrapolation of that graph, which is going to be a linear plot at C equal to 0, we obtain this transport at infinite dilution. Thank you so much.